All right, so we finished up with regressions on Chapter 8 is over population samples and probability. So there's some good news here. One, we've already been over some of the population samples, so some of this information will be more of a review. Also, there's no, we won't use SPSS in this chapter, so I think it's 8. We don't talk too much about 9. I think it's 10 and 11 are hypothesis testing, and then it's 12 before we get back to SPSS. So if you're like, man, I hate SPSS, good news. You won't have to deal with it for at least a couple chapters. So what, and we've talked about this before, what a population is a little bit subjective sometimes. So it could be all the students in the class, could be a population. There are other stats classes though, the exact same classes just with other instructors. So this class could be a sample of all students in stat classes in psychology at Northeastern. But stats class, it isn't the only class at Northeastern, so it could include all students at Northeastern. And then this class could be a sample for the population of students at Northeastern. Or we could take the students at Northeastern and use that as a sample for the population of all college students. So there's all kinds of ways that you can look at it. You just have to make sure to define it clearly for your readers, your audience. Attitudes towards abortion, SAT scores of currently enrolled students at Northeastern, that could be a population. All visitors to Disneyland on a given day, the ethnic backgrounds of all current employees at the U.S. Postal Department. So there's all kinds of examples. Those are populations. Samples are a subset. So yeah, the population is a complete set of observations or all potential observations. So like all currently registered voters in the United States is going to be a population. And if you get a small set of those, a subset, that is going to be a sample. So any subset of observations from a population. So for example, when you see statistics usually in the news, that's going to usually be a sample. So we're usually dealing with samples when we're doing statistics. So for example, the Bureau of Labor Statistics, their monthly survey that estimates unemployment, they're only getting about 1% of all the work sites included in that. So 1% of work sites are included in the monthly estimate of rates of unemployment. So when you hear the rates of unemployment, maybe not, it could be a little bit off. When they talk about samples for presidential elections, those are sometimes off. It's because they only get a small subset. And what they hope is that that subset represents the population, but it's not always the case. Just some other examples, like if we were just looking at students in the class, and if we were in a physical classroom, the students in the front row, that could be a sample of all students in the class. Students on the back row, that could be a sample of all students in the class. However, if you, when you're picking your sample, you again want to make sure it's representative of the population. And one way to do that is try to do random sampling. And so, it's the next one here. Random sampling is where you try to select all potential observations in that sample so that it represents the population. If I just pick students off the front row, it might not represent the population of students in the class. Or if I pick students just off the back row, it might not represent students within the class. It's a stereotype, but the stereotype is that the students that care more about the class sit in the front, and the students that don't care about the class sit in the back. It's a stereotype. It's not. There may be a kernel of truth to that. There are definitely some students that sit in the front because that's who they are, and some that sit in the back because they don't care. But I'm just saying it's not. It's a stereotype. There's a kernel of truth. But for our example, if I just pick the eager students that sit on the front row, it's not going to represent the entire population of the class. Or if I just pick students that are like, I don't care about this class, that's not going to represent the population of the class because it's somewhere in the middle between those two extremes. So you do want to have random sampling to make sure that if we were going to pick students from the class, we would do something like we would have like 30, we'd give everybody a number and we'd get, like 30 students I think are in the class, 35, and everybody get a number and we just randomly pick out the 10 that we wanted. And so, if you're student 11 or 14 and 21, that's the students that we would pick. Another example, so let's say you're trying to do a survey with Northeastern students and you pick students, you go to the student union and that's where you get your sample from. Think about it. What would be the problem with that? If you're wanting to get the population for Northeastern students, like something about their attitudes, and you go to the student union and that's where you get your sample from, what would be the problem with that? Just think to yourself for a second. The problem is that if you go to the student union and that's where you get your participants from, it's only going to represent students that go to the student union. There's a lot of students that don't ever go to the student union. And so you completely ostracized those students from your study, and you're just getting those students that go to the student union. That actually wouldn't be random sampling. Okay, so we got random sampling, meaning that you're trying to get a random sample that represents that population. There's also random assignment. Try not to get them confused, but with random sampling, it's about getting our participants for our study, how we're getting those. With random assignment, this is where we are going to assign them to one group or the other. When we're running a true experiment, we have a manipulated independent variable, meaning that us, the researcher, we manipulate that IV, and then we put people in one group or another group. It could be a whole bunch of groups, but just for this example, we'll just say there's two. A drug study is a pretty good example. So you create this drug, let's say it's like anti-anxiety drug, and you create the drug, and then you're like, okay, so we are going to randomly assign participants to either be in the drug group or the no drug group, maybe a placebo group, or the control group, another way to put it. So we're going to randomly assign. You have an equal chance either being in the drug group or in the placebo group. The point being, I should not, as a researcher, choose who goes in which group. If I was like, I think these participants would really benefit from taking the drug, I'm going to put them in this one, and the other people in the control group. That's a confound. You've totally messed up the causality. But that's what we're trying to do with a true experiment. We're trying to say that this drug causes anxiety to go down. But if you fool around and handpick, cherry pick participants to go in the group, you're messing with that causality, and so you don't want to do that. Okay, so yeah, this is another way to put it. Random sampling occurs in well-designed surveys, and random assignment occurs in well-designed experiments. The other part of the chapter, we talk a little bit on probability, and so this will be some new information here. Probability is the proportion or fraction of times that a particular event is likely to occur. So if you flip a coin, there's a 50% chance it's going to land on heads, or a 50% chance it's going to land on tails. That probability is expressed as 0.50. So a fraction proportion for heads or tails is going to be 0.50. Another example, so the chances of having a birth in the month of December, how you would get that is there's 12 months. We're looking at 1 month, December, so 1 divided by 12, or if you want to put it as the proportion, it would be 0.08. So if you're having a kid, it's 0.08% chance that you're going to have a kid in December. This here is a distribution of heights for American men. It's a sample. I think it's like 3,000 men. We're trying to say that this sample represents the population of American men. So we have this sample. If all 3,000 were right here, and I just randomly selected one, I would have about a 2% chance of selecting someone that is 62 inches or shorter. So about a 2% chance. Okay, and so let's say we had a question like, okay, well, what if it's if we randomly pick somebody and it's 73 inches or taller? So we're here at if it's 73, exactly 73 inches, it would be a 5% chance. But what if we said 73 or taller? Then we're going to have to add these up. It's called the addition rule. I believe, yeah, here we go. The addition rule, where we add together the separate probabilities of several mutually exclusive events to find the probability that this one thing will occur. The one thing being 73 inches or taller. And so we just add them up. Here we go. So 5 plus 3 plus 2 plus 2, that is 0.12. So it's a 12% chance, we just randomly picked one of these guys, that we're going to get somebody that's 73 inches or taller. Also there, it says, mutually exclusive events. What that means is that events that cannot occur together, so you can't be 73 inches and 74 inches. Sometimes events, so it's clear cut with this case, 73 and 74. Sometimes the events are not mutually exclusive. Sometimes there's overlap there, and you have to do an adjustment to the addition rule when there is an overlap. I'll give you an example here. So here's an example. So we have students, stats class, seniors in the class, 20% of the students in the class are seniors, 70% of them are psychology students. What's the probability, if you randomly picked one, that it's going to be either a senior or a psych student? Now, what you would think to do is just do the addition rule and add 0.2 to 0.7 and to get a 0.9% chance. However, some of the students are going to be both seniors and psychology students, and so you have to adjust that addition rule to figure out if you just picked one or the other. And how you do that is you do add those two together, so the 0.2 and the 0.7, you add those, and then you subtract the third possibility. So 0.2, 0.7, that's 9. The third, the option there is the 10% that's there, and so you would take your 0.9 minus 0.1 to get 0.8. So it would be chances of picking one, 0.80. So there would be an 80% chance if you just randomly picked a student in the class that you would get either a senior or a psych student. The multiplication rule, we have the addition rule, then we have the adjustment for the addition rule, we have the multiplication rule. This is several independent events to find the probability that they would occur together. So back on our height example, what are the chances that one random guy that we pick out of this group would be 73 inches or taller would be 12%. We talked about that earlier. So if we asked a question like, what's the probability of picking two men that are 73 inches or taller? So we're going to pick two together. So we'd need to, that's two separate events, and we have to use that multiplication rule. The chances that the first man will be 73 and the second man will be 73. You just multiply those probabilities to get that. And so in this case, that 12%, take 12 times 12, and that becomes about a 0.01. So there's about a 1% chance that we would randomly pick two guys, 1, 2, that are at least 73 inches or taller. Clearly that number, 1%, is much lower than 12%, but that makes sense. Because if we're just picking one, sure, 12%, that makes sense that we pick one. But if we're going to pick two in a row, that is going to be, that would be much less likely to happen that you'd pick two in a row. And so that's why that number is much lower. It goes from 12% to 1%. So yeah, the combined occurrence of two events is less likely than it just happening once, which hopefully that makes sense. The independent events, this is where one event has no effect on the probability of the other effect happening. And so like with the guys picking the height, those would be independent events. You pick one guy, that's not going to affect the next guy that you pick. Because an independent thing, they're not, those two events wouldn't actually be related. Or like, let's say you have a kid, let's say you have a daughter, and then you get pregnant again, you're like, oh, well, this time we'll probably have a boy because we had a daughter last time. Nope, that's not how it works. It's still 50-50. It's like the coin toss. They are not, each time you flip the coin, it does not depend on the flip before. It's kind of some gambler's fallacies where they'll, if it lands heads, you think, oh, well, it's going to be tails next time. Nope, it's still exactly 50% that it's going to be heads or tails. So like flipping the coin, independent event, sex of your child, independent events. There are times though we have a conditional probability where they do kind of depend on each other. So the height of two randomly selected guys that we picked, independent, they're not related. However, if you got the height for two brothers, two guys that are related, that is going to be dependent or conditional. If one of them is tall, it's not necessarily true that the other one will be tall, but there's a probability that it could be because they have the same genes. Some other like conditional probabilities, if you get an A on the midterm, the probability that you would get an A in the course. And so those two things would be linked. Although, like, so if you're a psych student, that you get an A in, developmental psych, it doesn't mean you're going to get an A in chemistry. Those would be two separate things. But in the same class, the midterm grade is probably going to be fairly reflective of your final grade. If you finish 2 years of college, you'll probably end up finishing college. Those are going to be conditional and they're going to be related. We can get to some probabilities through kind of doing frequency distributions like we've done in the past. So in this example, for one of the examples from the textbook, they say that 100 couples have undergone marriage counseling. And 60% of those say that they're as improved. So 60% of them say that they're we're going to have 100 here for the total. 60% say it's not improved. Or, I'm sorry, 60% describe their relationship as improved. So we have that. So that means that 40, since we have 100, 40% say that theirs was not improved. For the group that was improved, 45 couples had children. So 45 had children, which means we're going to have 15, because it's going to add up to 60, I believe. And then let's see. Of the group that would not improved, 5 had children, and so that means that 35 did not. And so then we can, extrapolate this out if we'd like. That means that 50 of the couples have children. Oops. And 50 don't. So again, just to kind of reiterate what we got going on here. They go to a marriage counselor. 60% of them said that their relationship was improved. 40% said it's not, out of 100. Of the 60%, 45 of those couples had children. 15 did not. For the ones that were not improved, 5 had children and 35 did not. So, what is the probability of randomly selecting a couple who describe their relationship as improved? 60. So this is pretty easy since these are divisible by 100. What's the probability of randomly selecting a couple with children? So that have children, we did have to add those up, so it's 50 right there. What is the conditional probability? This is where it gets a little tricky. What is the conditional probability of randomly selecting a couple with children given that their relationship was described as improved? Okay, so what is the conditional probability of randomly selecting a couple with children? Okay, so have children right up here. Given that their relationship was described as improved. So we're looking here, they have children and it's improved, so it's 45 out of 60. 45 out of 60, that is going to be a 0.75. So you would just divide 45 by 60 and get 0.75. The conditional probability of randomly selecting a couple without children, okay, no children, given that the relationship was described as not improved. So no children, not improved, 35 divided by 40, you get about a 0.88, 0.75. All right, and what's the conditional probability of an improved relationship, okay, given that the couple has children? Okay, so we have conditional for an improved relationship that they have children. So to get this, that have children, we have a total of 50, the 45 plus 5. The ones that described it as improved was 45, so it would be 45 divided by 50, which would be 0.90. So 90% of the couples that had children have found that their marital status was improved by going to therapy. Okay, so that is it on Chapter 8. Again, it's not that difficult. It's a fairly straightforward chapter. We won't do a whole lot on Chapter 9, and then Chapter 10 and 11 are on hypothesis testing, which is I think it's great stuff. Definitely need to know that for your future in psychology, in my opinion. And it'll definitely help us. It'll set the groundwork for doing the t-tests and ANOVAs that we'll do here in a bit, in a few weeks. And it'll also, if you didn't quite grasp some of the stuff with the regressions, I think when we talk a little bit about the hypothesis testing, that'll help a little bit with that too. All right. Thank you very much for listening.